Oh, so you go back to like this drawing right here. They like shared. Or no, this one they shared the.
Yeah, well, what we're showing here is we're sharing 4 electrons, okay, and we're showing two electrons here.
Okay.
So this really has very little to do with this,
Okay.
because this is just how do we get them to work out, and this is what does it actually look like when we get there?
When we get to where?
When we get to the shape of the molecule.
A wiener?
Not there. We're not there yet. Yeah. Well, okay. The bond looks like a wiener. Yes. Okay. Good. All right. All right. Now let's look at what happens then between the nitrogen and the oxygen. Okay. So I'm going to kind of stay over here a little bit to show that. Here's our nitrogen. So our nitrogen's got one hybridized orbital coming out like this, and the oxygen's got a hybridized orbital coming out like that, and they're going to overlap to form a sigma bond. Okay? Alright? They're overlapping to form a sigma bond. And of course then we get it narrowing down into our sort of cigar or wiener shape, and there's the sigma bond, right? But remember, a sigma bond only accounts for 2 electrons. One from oxygen and one from nitrogen. That would be like these 2 electrons we're sharing here. We need 2 more electrons shared.
So that holding happens again?
Not that thing. We have to have a different shaped bond. And here's why. Remember, our sigma bond is directly on the line between the 2 nuclei. We can't put another bond between the 2 nuclei because that's the same space and you can only get 2 electrons there. What we need is a way to build a bond that is sharing electrons between these 2 atoms but is not in this space. So this is where we need p orbitals that are not hybridized.
So the other one's not a sigma bond?
The next bond we make between the oxygen and the nitrogen is not a sigma bond. That's correct.
Because you can't have more than one?
In the same space.
Okay.
Okay? So let's go back up here. Here's our p orbital that's not hybridized on the oxygen. Here's our p orbital that's not hybridized on the nitrogen. Okay?
Okay.
Now these are also going to reach out and touch each other. They're going to, you got both, so hybridized orbitals look like a single node. Unhybridized orbitals have what looks like 2 nodes. Okay? So when they reach out and overlap each other, okay, we're going to get a pi bond that is in 2 parts, going across the top and going across the bottom. That makes up a 1 pi bond, okay? But it has 2 parts. Pi bonds have 2 parts.
So they're just that big that they run into each other?
Yeah, you can say it that way. Okay?
And then these are pi bonds, right?
These are not pi bonds plural. This is a pi bond.
Oh yeah.
Both of these together make up one pi bond. This is both 2 parts of the pi bond.
Okay, because they come from, like, this is the same node and this is the same node. So when they join.
Think about a hot dog bun. Hot dog bun has 2 parts, right? Well, this is a pi bond that has 2 parts.
And they're still connected.
Okay, they're still connected.
Okay.
You know, there's no sort of a connection like that, but they're part of the same bond.
Yeah.
Okay? All right. So then when we have our molecular structure then, I've got to have this sort of thing going to the oxygen. Okay, so here's our sigma bond going to the oxygen. Okay?
Can you draw at kind of any angle? Like, does it matter that?
Well, I'm just trying to sort of show the way it actually works out. Okay? Now, technically, I should take the pi bond and instead of having it flat on the paper, I should turn it like this because I want to get it away from this lone pair. We're not going to get too complex with it, okay? We're not going to get that complex in here. Basically, you just need the pi bond out here at this point, okay? It's only when we do double bonds I expect you to be able to show them, you know, and going opposite each other like this, okay? So that was pretty sloppy drawing it there, but that's our pi bond, okay? Then the oxygen, if we go back to our Lewis dot formula here, okay, the oxygen has 2 lone pairs on it. So we need 2 of those hybridized orbitals making a lone pair over there. The chlorine has 3 lone pairs on it. If we want to get really complex and detailed about it, okay, so there are 2 lone pairs on the oxygen. Those have to be hybridized orbitals. 3 lone pairs in the chlorine, that has to be hybridized orbitals. I'm not going to expect you to be able to draw all that on a test, okay? We'll keep it a little bit simpler than that. I may ask you to do double bonds, triple bonds, but I won't try to do all that stuff, okay? I may have a drawing on a test and ask you to interpret it, but I won't ask you to draw it yourself, okay? Again, I don't expect you to be an artist, okay?
Okay, so
But that's a pretty good drawing you got there. Yours is better than mine.
So when you do have like two pi bonds.
No, 2 parts of the same pi bond.
Yeah, but when I'm saying.
Oh, okay. When you do have 2,
yeah, when you do, then that would be.
I got to have another set of those.
But why would you need two bonds? That'd be
Because
like if you had 4.
Triple bond.
Oh.
Okay. Let's see. What I'm trying to think of a triple bond that we haven't done. Well, actually, we've done just about all of them that are simple enough to do in this class. I kind of hate to cover the same territory, but let's do it anyway. All right. So here's C2H2. So starting with our Lewis dot our electron dot formulas, we got 2 carbons and 2 hydrogens. Now I'm going ahead and put them together like that because I know the direction they're going to go in.
Yeah.
You don't have to lay them out like that. You can still figure it out. Okay. Well, the hydrogen only needs 1 bond or 1 shared set of electrons. The carbon then, to make all this work out, if I only got 2 carbons and 2 hydrogens, has to have triple bonds between it. Okay. And so we're going to have a triple bond, 1, 2, 3 sets of electrons between the carbons. When I get to our Lewis dot formula. Okay. No, that's a C.
Oh.
You want white out?
Sure.
It's kind of getting gummy, but it'll still work. I need to put some alcohol in it or something to kind of get it to. Might want to let that dry before you redraw that.
Yeah.
Okay. Although you can use a pencil and it'll just kind of work its way through there if you want to. Yeah, use that kind of pencil, because if you use a mechanical pencil, it'll gum up the mechanical pencil, so that's good. All right. So in this case then, we don't really have to worry too much about the molecular shape. It's going to end up being a whole linear thing, all right? Because it just has to. That's how you get. The only way you can get this set of electrons as far apart as you can from this set is if they're on opposite sides. So there's 120 degrees between here and here, 120 degrees between here and here. The whole thing's going to be linear. But what we want to look at here is the triple bond. Okay. So here's a carbon, and here's a carbon. Got to have 3 bonds. All right. So our single bond. Remember, you always have a single bond, is directly on that line between the 2 nuclei. We don't have a stick. Okay? You have to have 1 pi bond that's going across the top and bottom here. Okay? Remember, and the reason we have to have a pi bond for the second bond is because you can't put those electrons in the same space. They can be parallel to each other, they've got to be separated a little bit. Well, if I'm going to have a third bond, it's also got to be a pi bond, and it's got to go front and back like that.
So the sigma bond always counts as 1 bond together?
Sigma bond's 1 bond.
Okay.
The pi bond has 2 parts.
So you always have 1 less pi bond than you do the actual bond. That didn't make any sense.
Not to me.
You always have, like, here, in this one you had a double the so you had 1 pi bond. Like, in this one you have
2 pi bonds.
2 pi bonds.
And that's the one that's so hard to draw on a piece of paper.
Okay.
Because you got to do it somehow to show that perspective we were talking about earlier. Okay? And the only way to do that sometimes just doesn't make sense to students when they see it. So that's why we did the balloons. One of the reasons we did the balloons. Because when we do the pi bonds and the balloons, you can see that one set of balloons going around top and bottom and the other is going front and back. If you look at the video on the website about the balloon shapes, you'll be able to see what I'm talking about. But if I'm trying to draw it, then I've got to kind of arrange it so that, you know, if you have a little bit of art, you might be able to tell what's going on. Okay. You can imagine it's taken me a long time to figure out how to do that.
Yeah.
Okay, and it's kind of tricky. If you haven't had art, if you're not good at that, it's kind of hard to figure it out. But I don't expect you to be a perfect artist on this stuff. Okay, just have a reasonable representation and understanding of what's going on. Okay, so that's our triple bond. In this case, we've got a single bond here, this part right here, and this part back in here make up one pi bond. Okay, so those two parts make up one of the pi bonds. That's a y. Let's just call that pi y.
So it's like one from in front and one from behind.
Yeah. So these two parts here are 180 degrees apart from each other, and these two parts here are 180 degrees apart from each other.
Okay.
Okay. So then we could call this one pi z, I suppose, and that would be this node right here and this node down here. Okay, those two make up the other pi bond. All right, and then you got this sigma bond here. Single bonds are sigma bonds, and that's going. It's like out here like that. Okay, that's another sigma bond, and we got a hydrogen over here.
And because they don't have any lone pairs, then you just don't.
That's it.
Okay.
Okay. That's why I color code them when I do them in class. And you've got a drawing like that. I saw yours.
Okay. Yeah, I get it now.
You think?
More now.
Good.
Yeah.
Good. Well, I appreciate you coming in and getting help with that, and give me a chance to record this, and maybe help some other students.
Yeah. Yep. I think that's the only problem I have with most of
Is
it.
it
Like,
figuring out the shapes?
yeah. Sometimes I'm more of a memorization person.
And I understand that. In fact, there are people who are good at that sort of thing, thinking in 3 dimensions, and people that aren't. But people that aren't just find ways to deal with it, And we were talking earlier about people who have disabilities. There are a lot of students with disabilities that you never know because they've learned to work with it.
Yeah.
It takes more work for them to do the same stuff you and I do sometimes. But they don't want anybody to know they got a disability, and they found a way to work with it.
Yeah.
There are a lot of people who are very intelligent, but they have disabilities, and you don't know it because they found a way to work around it. Some of our best chemistry students have disabilities.
Really?
Oh yeah, and because the funny thing is, because they have disabilities and they've been forced to work around or they wanted to look like and feel like everybody else, so they work around it. They work harder, but it's made them think in ways that you and I don't have to think. They can see this stuff easier sometimes. It's just amazing what sometimes having to work hard actually can build more skills than not having to work hard.
Yeah, I know a girl who has a problem, and for a while they had her in like special classes, but now they moved her out because they realized how smart she is, and now she's in like all honors classes, and it's like crazy.
And it happens. It happens. I mean, you look at all the great scientists in the world, a significant percentage, I wouldn't by any means say most of them or anything like that, have some kind of disability. Because they've been forced to think around it, and it makes them more of a creative thinker. And so they think in ways that we don't think, and they figure out problems because we don't think about it that way,
Yeah.
And it happens there are a lot of honor students who will go to college who've never had to work very hard because they just got through all these classes and they breeze and they read the textbook. They don't study much. They go to college and they hit a class that's like that. That's their brick wall. They hit that brick wall. And they can't get past it because they've never had to work hard. There's something about having to work hard sometimes.
Yeah, like that class that you said you took with that one.
Organic chemistry.
Yeah.
Oh man.
Is it so hard?
It was so hard.
Oh.
So hard. But I worked really, really hard and made an A. But I had to work. There were other people in that class a lot smarter than me or could figure it out easier than me or something. They didn't have to work as hard as I did, but they didn't make A's.